So today we are starting a new chapter. It's about uniform boundedness principle and the closed graph theorem. So to start with, we need some, so those are topological results. So to start with, we are going to present first the Baire category theorem. So the Baire category theorem writes like that. So the general setting is you have a metric space which is complete. And you have a family, but indexed by n. And you assume that for each fixed n, the interior of this closed set is empty. For example, in a metric space, a point satisfies this assumption because a single point in a metric space is a closed set, and its interior is an empty set. Or, for example, if you have r to the n greater than 1, a single line. So you take a closed single line with the bounds, and then it's closed, but its interior is empty. Okay, but so if you have a family indexed by n, and if each interior is empty, then you can conclude that I'm sorry. That's so sorry for this interruption. And so the conclusion is that, in fact, you take the union of all these sets, and the interior of the union is empty. So a simple and good example to illustrate that is when you for example, you put some points in R or R to the n, then you took the union but indexed by n of the points. It has an empty interior. So you can understand that for in R or R to the n, and we are going to give a proof of that. Any question? So the proof of the Baire theorem, let's first give the ideas. So there's two main ideas in the proof. First, so we are working with open sets. So we are working with the complement. So by definition, in a topological setting, a set is closed if its complement is open. And so we are working with the open sets. And so the conclusion of the Baire theorem Sorry again for this interruption. So what I was saying is that so the conclusion is we want to prove that here the union of the closed set, the interior of this union is empty, which is to say that is complementary is X. Okay. And so the first part of the proof relies on the formulas that gives the complementary of the closure of a set is, and you make the relationship with the interior of the complementary. Okay, that's the first part of the proof. And then, so this primary work allows us then to prove that some intersection of open sets are dense in X, and to do that we are going to construct a sequence to prove that we have density. So those are the main ideas of the proof. All right, so let's start with the first part of the proof. So let's have a look again at the theorem. The theorem is here. You assume that every interior is empty. The interior of Fn is empty for each n, and then your conclusion is to prove that the interior of the whole union, but indexed by n, is empty. All right, so as I said, you first start by working with open sets instead of closed sets. So you call un the complement of Fn, which is an open set because Fn is a closed set. Next, let's see if you know this formula. So I will just hide this. So can you remind? Do you know so you should know the closure of the complement of a set. Can you put that as interior and complement? Let's write that on the board. So first thing, do you remind? Can you write me? So the closure of UN is by definition the closure of the complement of Fn. And there's a formula. Do you know the formula for that? So let's assume I have a set, whatever this set E is, just a B. If I look at the closure of the complementary, so it's everything that's here and with also the border here in R2. And so this is equal to, I just switch. I switch. It's the interior of the complement of the interior. It's the same. right? So if I have a set B, I take the complement of B and the closure is the same that to look at the interior of B and to take the complement. Okay. All right. Okay, but so what's the assumption? So let's just continue with that. What's the assumption here? This by assumption is X. And okay. And what we want to prove is that the union of all the Fn when I take the interior is empty. So this is the same that's proving that I will take again the complement of that and I apply the same formula. So the as I said, you have that. This is the same as that. Okay, classic formula. You can prove it, but it was done in undergraduate classes of topology. Okay, so I apply this formula here. What do I get? I get union and that. So, and this is the same thing as the intersection on n of the complement of Fn, but in our case it's un. And when I take the closure of that, I must have x. So that is to say that we want to prove that the intersection of the open sets U1 is dense in X. Okay, so if I prove that, the Baire theorem is proved. So again, to summarize what we did, so we just finished the first part of the proof. So we work with closed sets, and what we did, so if you assume that the interior of each given closed set is empty, then your conclusion is that the interior of the union, but the union, you must to be careful, is indexed by n. Of course, this doesn't work if this set is not n, but another set, it might not work, okay? But now, the first step in the proof is to go from working with closed sets to work with open sets. And so by using the formulas with complementary and closures and interiors, this conclusion transforms into that the intersection of UN closure is equal to X. That is to say, we want to prove that the intersection of the UNs is dense in X. Okay, so that's what we are going to do. Okay, so this is the next step of the proof. So now our problem is to prove that the intersection of the UNs is dense. So let's O be any open set in X we want to prove that there exists X in X such that X belongs to A, I call, so A is just this set, and it's also in O. Okay, if I prove that, this means that A is dense in X. Okay, you look at the definition of density, it falls in that. Okay, let's do that. So so we are going to define a sequence such that the limit of the sequence will be there. So we will exhibit such an X has a limit of a sequence Xn to be defined now. So I start. So first, so I choose X node that belongs to A. No, it's not that. To A. It's not A, sorry. It's. So you know what I have? I have a sequence of open sets. So I want to construct a sequence that will belong to each open set. And also I need to stay in my first open set here. Maybe, so I have an open set, and then I want to construct a sequence such that the sequence will be inside all the U0, U1, etc. So I first start with, I want that X0 belongs to U0 and O. I can do that. Why? Because U0 is dense in X. So for each open set, I can always find a point in there. And even more, since those two are open, I can ensure that I have some, this is open, this is an open set. So I can ensure that there exists a R node such that the ball, and I want a closed ball, I can always do that, is in, so let's, is here in, is that clear? Is that clear why I can do that? Okay, this is the key point of the proof, and it is worth to do it clearly, and that almost everybody understands it. So I can do that. I can do that because U node is dense in X, and since I work with open sense, I can put a ball like that. Okay. So now I will define X1. So BC is the closed ball. So the closed ball of center X node and of radius R node. Okay, but then what? Then what? Then U1 is dense. So there exists X1, which belongs to I can take it in the open ball intersection with U1. I can do that because U1 is dense. So when I is dense, so so I can find this is the definition, right? You have to understand why. Okay. Okay, so I will construct the sequence like that. Okay, and so and also R1 such that now the closed ball of X1 R1 is included in this same. Okay, so by doing that, assuming that we have by induction, I do the same and I will construct my sequence Xn such that so here it's n Rn okay. Okay, so what can I do about this sequence? So now I defined. So Xn is now defined. What can we do? What can we say about this sequence? Does anybody has an idea? So what assumption did I not use until now? So what we know is that X is complete. So every Cauchy sequence converges. And you know what we did, we have these balls that are included one in other. And so you have no choice. This the sequence is Cauchy. they are included. So if I choose an n, every point xn is in the ball. So if I choose a ball with n large enough, the distance between any element of the sequence will be less than the diameter of the ball. So this is Cauchy. Okay, you can think about it. Okay, but X is complete. Therefore, there exists L in X such that my sequence Xn converges to L. Yeah, I call it X. Yeah, we can call it X. We can call it X because I called it X at the beginning. All right, but so we have to notice that for n or for p greater than n, we have to notice that xp belongs to the closed ball of xn Rn, and this is closed. Okay, so this means that so now xn belongs to the ball. Let's start at one. The ball, the closed ball of center xn. So it's not. It's what I want is L is X. The limit here now. I want the limit here. So xn Rn, which is included in by construction in O intersection with U n minus 1. That's how we constructed the sequence. Okay, so that's it. So therefore, X belongs to the intersection so and this ends the proof.